Bismillahirrahmanirrahim. Now our next theorem that if W is a subset W of a vector space V over the field F is a subspace of V if and only if W is non-empty, and the second condition satisfy that for each two element U and V in W, U minus V contain in W, and for each element per each scalar A belong to the field F, and each element of W, the operation, the scalar multiplication of the scalar with the element of W, which are the element of the vector space V. In this case, U is a vector. The scalar multiplication of these two elements belong to W. Then this condition will be satisfied if only if W is a subspace of V. Suppose that W is a subspace of the vector space V over the field F, then W with respect to the binary operator addition is an abelian group and is a by the condition of the vector space subspace W will be a subspace of V if only if W by itself over the field F is a vector space. In the vector space, the additive addition will be a binary operator on the vector space, and that vector V will be an additive abelian group. Since W is a subspace of the vector space V, therefore W also satisfy the condition of the additive abelian group, and W is a subset of the vector space V. Therefore, this group is a subgroup of the vector space V of the additive abelian group V. Therefore, W passes at least one additive identity element. Since W satisfies the condition of the additive abelian group, therefore W contain at least one element which is the additive identity element. That is, W, the additive identity element in the vector space V is the zero vector. Therefore, the set W contain at least one element which is the additive identity element of the vector space V, because W is an additive abelian group. Now to prove the next part of this theorem, that is, for each UV belong to W, U minus V belong to W. Consider W is a subspace of the vector space V over the field F, and U and V are any two vectors in W. Then the additive inverse of V is also contained in W according to the condition of the subspace of the vector space V. Now, U minus V is equal to U plus minus V, that is, U and minus V are the elements of W, and W is a subspace of the vector space V. Therefore, the addition of any two elements of W is also contained in W, and U plus minus V, U and minus V are the elements of W. U plus minus V is equal to U minus V, that is, U minus V is also an element of the vectors of the subspace W. And the third one condition that to prove that for any scalar A and any vector U, the scalar multiplication of the scalar A with the vector U contained in W. For each scalar A in the field F and any vector U from the W, where W is a subspace of the vector space V, A multiplied by U contained in W, that is, W is a subspace of the vector space V over the field F. Therefore, the scalar of the field with the elements of W, the operation of the scalar multiplication of the elements of the field with the elements of W is contained in W. To prove the converse of this theorem, to prove the condition first, second, and third is satisfied, then we have to prove that W is a subspace of the vector space V. to prove that W is a subspace of the vector space V over the field F for any element X belong to W. Since W is non-empty set, therefore there exist in elements in W, these elements belong to the vector space V over the field F, which satisfy the condition that all the elements of W contain in V. Thus W is a subset of the vector space V over the field F.